Okay, thank you very much. Yes, my name is Joris. We'll talk to you about what you see there, and I would like to thank the organizers of this committee to switch around and bring it all online and to give me the stage here. So let's get started. This is the slides of the contents, and instead of bullets, we have this nice illustration made for us by an illustrator. As part of one of the projects or sub-projects of this project of an inertial sensor, and this is what we're going to talk about: the inertial sensor itself, the actuators, its readout system, etc. And why do we make such an inertial sensor? For a gravitational wave detector, and it's a plural, so we make it actually for both Einstein telescope and the lunar gravitational wave antenna. But before I will introduce those, we'll first talk about gravitational waves themselves. So here I will show you part of a movie that was made at the time of the first detection, and it will give you a flavor of what gravitational wave detection is all about in 30 seconds. So here we go. You see there are two black holes spiraling into each other, becoming one, sending out a pulse of gravitational waves. This pulse then, after a large cosmic travel of sometimes billions of years, traveling billions of light years far, arrives at Earth and makes the Earth wobble. Of course, this scale of is largely exaggerated there, because we need these things, large interferometers like LIGO and Virgo, that will then this doesn't go well. Anyway, I wanted to show this. So you can see there the stretching and squeezing of the arms, and that gives us these flashes of light, and that's our signal. There we can say, we've detected gravitational waves. Well, this stretching and squeezing of light, if you translate that to the mirror motion itself, then it's this tiny fraction of the Earth's ever-present motion. And that's a problem, because you have to do something about that. So what do we do about that? We hang the mirrors up. We hang the mirrors such that we decouple them from the Earth's motion, and we can look at how such a suspension behaves, and it does so as a harmonic oscillator. And a harmonic oscillator, of course, has a resonance frequency, so here I can explain you how that works in this particular case according to this graph. So here you have the line of the transfer function of, let's say, the top, where it's attached to Earth, and the motion of the mirror itself. You have the dotted line that is 1, so the transfer is 1, no attenuation, no amplification, just a transfer of 1. Above the line is the mirror moves more than the Earth, below the line is it moves less than the Earth. Of course we want to be in this region, but before we're there, and this is what I always call the price we have to pay, is the resonance frequency. So there you get amplification, the mirror moves more there than your input motion. But once you've paid that price above that certain frequency, it goes down with 1 over the frequency squared. And then you get the attenuating behavior that you see there. The mirror is not moving along with the Earth, so it's decoupled. So of course we don't want to pay that price, so we damp the resonance frequency, and in that way, we don't pay that price and still get the decoupling behavior. But we need sensors in order to sense this and damp it. And we also would like sensors to monitor how well this is going, because of course there are all kinds of internal modes of real mechanical systems. So you want to be sure that that's actually happening. So in reality, of course, we don't go with 1 over f squared. We couple these things. So we get these large chains. Here you see the one for Virgo in Italy. So here you see the mirror, and then attached to it is a 8-meter long structure of all kinds of mechanical filters. But that also means that if you want to put a sensor here at the bottom, you need a very good sensor, because it's so decoupled that it's so vibrationally quiet that you cannot rely on commercial sensors anymore. So we need our own sensors, and this is one that I developed during my PhD. This is one at room temperature, so no cryogenics yet, but I can explain the general gist of how such a sensor works. So we have a frame. We put that frame on top of where we would like to measure the vibrations of. In that frame we suspend what we call a proof mass, and because of the inertia of the proof mass, it will lag the motion of the frame a little bit above the resonance frequency of this system. And so if you then attach a position sensor that monitors the differential motion between the frame and the proof mass, then you're in business. Then you have a vibration sensor. In this case, we like interferometers, so this is a centimeter scale interferometer, and this was done in feedback loop, so you also need a little actuator. This was done on a very quiet optical table because it was suspended. You see there in the back the suspension wire. If you want to know more about that, then you can follow this link here. Here you see a bit more schematic. You can see that we read out both arms of the interferometer via the second beam splitter here at the top, and we do that to get rid of all the common mode noise. For example, if you have intensity noise on your laser, then you will have that on both photodiodes, and by subtracting it you get rid of that. So here you see the final result of my PhD, but also of this sensor so far. You can see that we put two sensors next to each other, a commercial one, the L4C, and this accelerometer. So you can see that they're measuring the same. This is the last mode of the suspension. It's damped, so it's not a peak, but more of a bump. Then the commercial sensor hits its noise floor, and the blue line is our result. And our result reaches 8 femtometer per root hertz from 30 hertz onwards. That's really nice, but I have mixed feelings with this result, because you can see here, for example, this is what we modeled, and we didn't make it. I was hoping that this blue line would just hit this cyan line and then hit the shot noise level. So what is the matter there? The issue here, I think, is that there was still some residual motion of the proof mass, making this. I don't want to go into the detail, but the bottom line there is that the subtraction didn't work as well as I hoped. And the other thing that I would like to improve upon is this thermal noise. Well, thermal already sounds like you could solve that by doing cryogenics, and that is indeed what the plan is. So we set out to update this thing, and we have to lay a new puzzle now. So this is one of the things that I would like to add. Add another readout. So on top of that interferometric readout, add a more large range device like this. This is Rasnik, widely used in CERN for muon chamber alignment at Atlas or LHCb, for example. And if you attach all of these components and you move the mask, then you can actually see the mask motion on this camera, and thus get really precise measurements. Up to now 7 picometer per root hertz, but we feel that we can, with the upgrades that are upcoming, we feel that we can reach picometers or lower even. Something else we upgraded from this interferometric readout, we went to one with polarizing optics, and this makes sure that instead of, for example, here throwing away half the light, all of the light now ends up at the photodiodes. And this is a good idea because if you want to go cryogenic, you don't want to dump heat everywhere. So we set out to do that, and here we have a calibration result of moving this piezo while this mirror is stationary, and you can see that we indeed see the fringes. Something else that we have to do is in cryogenics we have to develop low noise readout electronics. So this is a collaboration with the KU Leuven. You can see here that indeed it's a good idea to go cold. This is a dark noise measurement, so that's better. Here you can see some other advantages or also challenges that we have to do. We read out with this so-called chopper stabilization architecture, but we also need part of it because we are going to use quite high currents in order to actuate. We need to do this kind of thermal measurement. So a little bit about the chopping architecture via these graphs here below. I'll try to explain it, and you can follow along in this thing here, in this schematic here. So you have a signal, then you modulate that signal. so that you will have most of the noise at low frequency and the modulated signals at the modulation frequency and some harmonics. Then you demodulate so that your signal again goes back, but your noise stays at these modulation frequencies. You low pass filter it, and you end up with a low noise signal. And all of that goes into this cryogenic. So that's another puzzle piece that we need to have. Then the last puzzle piece here is, like I said, thermal noise was an issue. We can go cryogenic, and that solves part of the problem. The other part was using stationary magnets alongside moving metal objects, which caused eddy current damping. And this is an issue for us as well, because then the quality factor goes down, and this makes your thermal noise go up. So we wanted to go to a magnetless solution. So we go for a superconducting coil, seeing a superconducting surface, and the magnetic field cannot penetrate that surface because of the Meissner effect. Hence, we can push this surface. So we have a push-only actuator, and we shall see later that that's why we need two of them. Together with the company, we're building these thin film devices. Here you can see the first strips for testing. We also do that with KU Leuven, together with the University of Camerino, who do more the theory side. We can come up with all kinds of nice simulations about that. So here you see all these puzzle pieces together. It looks a bit like the other one that I showed you, but now we have these two actuators. The Rasnik has been added, and this polarizing interferometric readout, and the custom cryochip. You can see that the puzzle pieces don't fit exactly right yet, so that's still under development. But yeah, this is what we plan to build. So what do we want to build this for? One of them is the Einstein telescope. So this is something that will be built in Europe, somewhere underground, and part of it will be cryogenic, the low frequency part of the detector. It's a large 10-kilometer triangle underground, and here you can see the first designs of the suspensions. Of course, now we need to cool those mirrors, so if you touch your refrigerator, that thing is vibrating. So you want to do something about that. So you want to suspend that the cold finger, as it's called, as well. So here you see a suspension just for the cooling part of it, and here a tiny last suspension to then attach it to the last stage, which is also cryogenic, because this part is then cryogenic. I hope that person is out when they switch it on, of course. Let's zoom in there a little bit, and then we can see where we would like to place our sensor. Of course, we would like to see if that vibration goes well, because if we measure it in the room temperature, and then because of the modeling project it down, then you don't really see the impact of it. So that's where we would like to put our sensor, and that's also the sensitivity goal that we set out that we want to achieve in order to make a meaningful measurement there. So we can make it out of niobium, the sensor, or if we want to go even better, but much more complicated in terms of fabrication, we can make it out of silicon. And then you can reach these things. So if you compare that to the room temperature case from my CV, then you saw that we were shot noise limited femtometer displacement sensitivity from about 10 Hertz onwards. Now we would like to have that from about 1 Hertz or even lower. And that is nice, because if you then compare that to the displacement of the mirrors of Einstein telescope, then okay, that goes down to 10 to the minus 18 or 10 to the minus 20. So those things we can't reach, but we can put it at the platform upstairs, which I showed last slide, and then in that way monitor the mirror and at least monitor the impact of the cooling. So where do we test these sensors? Because anywhere where you put them on Earth, you're going to have a problem because you will only measure the noise of the Earth. So you have to put them on some kind of seismically isolated platform, but then they also have to be in a cryogenic environment. So we have to develop some very low vibration cryogenics. And this is an image from a funding proposal that we're crossing our fingers for at the moment. Something else that, thank you, 5 minutes. Something else that where we can put it, this is e-test. You can read more about it following this link. And this is a prototype research facility for Einstein Telescope, where we combine active platforms with passive platforms strategies for the first time. And we have a suspended cryostat, and yeah, it's all going to be very exciting if this works. But then we could put sensors here on this cold platform as well. One other thing that we look at is the lunar detector. So this is the Urania Observatory, which we could have walked by if this pandemic wasn't still among us, let's say. And then we could look at the moon and maybe fantasize about putting these sensors on there, because you saw the Earth wobbling in the first slides. But on Earth you cannot do this because the Earth has the oceans and tectonic activity. It's much too noisy. But the moon doesn't have that, so you can put these sensors on and directly measure this wobble. So where can you put them then? Well, the moon has natural cryostats at the South Pole or North Pole. In the craters there, the sun never shines because it just doesn't reach it. So they are permanently shadowed, and it's below comfortable below 40 Kelvin. So if you want to read more about that, then you can follow this link and see this big collaboration, which is growing. So how does this sensor then relate to gravitational wave sensitivity? So here you see that, but I don't have a unit here yet. Because if we put this sensor on the moon, then we use this large baseline of this massive body, which is the moon, and we get sensitivity improvements for moon's internal modes. So the moon, if you give it a big hammer, if you smack it with a big hammer, it will start to vibrate around the millihertz region, and you can get to these kinds of sensitivities. Well, these kinds of sensitivities, if you compare them to LISA, this is another proposal which is going to fly 2034 of measuring gravitational waves with these satellites with 2.5 million kilometers lasers between them, or the Einstein Telescope that we discussed before, then you can see that this is a nice bridge over these things. We look a bit closer to this image here of how it might look like when you put such a thing on the moon. You put that, if you want to have a long operation, then you would like to have it powered. Usually in space you do that with solar panels, but now you're in the shadow always, so how do you do that? Well, a possible thing that we're looking into is doing the solar panels on the edge of the crater and then beaming them in, and then putting here this array. If you would like to join this nice adventure, like I said, we're an inclusive international collaboration. So send me an email and then we can talk. Here I still have a slide of other things that are nice to do on the moon once you have these inertial sensors there. You can start prospecting for lunar mining. People think there's large swaths of helium-3 and rare earth metals, for example. Also ice, which is important if you want to live there permanently. And the moon, unlike the Earth, which is forever changing, the moon is not changing so much. So people are very interested in the lunar geophysics to understand the interior of the moon and the history of the solar system, etc. I'll end with this summary slide, where you can read what I'm summarizing, but I would like to point more out these things that we're really building these test blocks of niobium in the beginning, where we want to spark erode these kinds of pendulums in there, and on the other side we're using an old Watts linkage to look at to attaching a Rasnik to such Watts linkage and see how that works. And that was all that I had. Thank you very much. Yeah, it depends what you mean by prototype. So to have the whole thing together, and yeah, so the e-test that I showed you, so that suspended cryostat where we would like to put these sensors, that puts a nice deadline for us by itself having a deadline at the end of 2023. This is, yeah, sometimes I wake up and think, that might be tricky, but yeah, we're pushing hard to do it, to get it done before that. And I think it is realistic to say that that it's a couple of years and not something else. So yeah, that's my hope. Yeah, that's also a nice thing because there are yeah, it becomes like a two-way thing because we would like to do what we call a sound check, uh, which is a Pathfinder mission, where we would like to send a more simple inertial sensor. And actually, this thing, not exactly this thing, but a watts linkage with a Rasnik on it, and then not cryogenic, and no feedback loops. That is actually a good candidate to do that. And it's not only to show that we can do that and that we understand how to put a watts linkage and put a device there that can do that can do sub nano G while surviving 10G or whatever you have to bear when you do a launch. And then, but it's also interesting there to understand the seismic environment of a crater like that because the best measurements that we have of the seismic environment of the moon is done in 1972. So that's quite a while ago, and we would like to improve that to also improve our models, etc. So yeah, I think that's it. You mean names? I don't know. Well, I think it will be. We have some thoughts about it, but these plans are largely. Yeah, let me put it this way: these plans are largely thought up by physicists like myself and not space engineers yet. So we talk, of course, to space engineers, and we understand that the best way to deploy this would be a kind of robotic thing with kind of drones like things. But other than a couple of sketches, we're not there yet. We do see, if you look at all those commercial space things, we see the dollar per kilogram declining rapidly. So that's very good for us. To keep us in the usual promise that we make, like LISA and ET, those are like $1 billion or more projects, and we are more in the hundreds of millions of dollars, which is also not cheap, but still, it's you can objectively, or almost objectively say, it is a cheaper way to measure gravitational waves. Yeah. But yeah, it's always about which frequency range, because of course, from the moon we cannot do what we cannot do the science that they can do here on Earth, and vice versa. It's all these kinds of you cannot simply say we're cheaper like that, because you saw the spectrum, let's say. Of the moon, yeah, we aim to be online when those others are online, so that's 2035, those kinds of yeah. Yeah, thanks. Thank you.